Okay, let's show you how to evaluate some of these weird limits. Right here you'll see I'm going to talk to you a little bit about one of the most difficult things to understand by a limit is that the limit is not necessarily the same as the function of value. Many times the function will be undefined at x equals c, yet the limit will exist. Now, so what we need to do is learn some algebra tricks. The replacement theorem will actually let us bring in these algebra tricks. So let's look at what the replacement theorem is. Let me give you an informal statement here. It basically says if two functions agree at all points except possibly at one number c, then their limits, I used the wrong there, but anyway, their limits as x approaches c must be equal. A couple of ways to find an equivalent function are the cancelization or rationalization techniques. Now, these are the most common ways to evaluate those limits that when you evaluate them by just plugging in, they give you 0 over 0. So we're going to look at those techniques in a minute. Now, what the replacement theorem says formally is, it says let c be a real number and let f of x and g of x equal the exact same function everywhere except at c. Okay, now what does that say? What happens if that's true? If the limit of g of x exists as x approaches c, then the limit of f of x also exists, and the two limits are the same value. Now, let me set something up here, and I'll give you a real simple example to start you off with to show you this. Okay, so let's say I have this function, and let's say I want to find the limit of this function as x approaches 1. So we're going to say the c value is 1. Well, actually, you can see here that if you canceled x minus 1 here over x minus 1, you would actually get this function, we'll call it g of x, equals 3. Okay? But you can't say that f of x and g of x are equal everywhere. F of x and g of x are only equal if x does not equal 1. Because remember, if x equals 1, then this would give you 0 over 0, which is undefined. So, but the theorem doesn't say that they have to be equal at 1. They only have to be equal at all values around 1. And actually, since this is the x minus 1 over x minus 1 will cancel everywhere except at 1. So f of x does equal g of x everywhere except at 1. Well, based on that, then we know that the limit of g of x must equal the limit of f of x. And we can get the limit of g of x because g of x is just a constant. And so we know the limit of a constant as x approaches 1 is just that constant. So the limit of g of x as x approaches 1 is 3. So therefore, the limit of f of x as x approaches 1 must also equal 3. Okay, now if you graphed this, what you would actually find is this. So if you graphed f of x, you'd notice you'd get a horizontal line at y equal 3. But at x equal 1, there's actually going to be a hole in it right here. So there would be a hole in it at y equal 3, x equal 1. So you'd have a hole there at the point 1, 3. Okay, but if you graphed the g of x function, notice this function here would be g of x equal 3. This would be a function that's identical to this function everywhere except at 1 because it doesn't have the hole at 1. So therefore, as you approach 1 from this side or approach 1 from this side, it would be the same as what you would get if you plugged 1 into this function. So, or as you approached 1 from either side from this function. So basically, the two functions are identical except at x equal 1. And so when that's the case, then you can actually replace the original function with this new function. And that's the trick that we're going to use, and that's called the cancellation technique. And also the rationalization technique does the same thing. It uses the replacement theorem as well. So let's look at some examples. All right, let's take a look at this example. I think we looked at this one earlier, or maybe one like it. Let's say we want the limit of x minus 2 as x approaches 2. Well, over x squared minus 4 as x approaches 2. Well, if you plug 2 in, the top's going to be 0 and the bottom's going to be 0. Well, you can't tell anything from that. That's not going to tell me anything because that's an indeterminate form. So what I want to do is I want to see if there's a way I can replace this function with another function so that I can evaluate the limit. And so what I'm going to do is I'm going to see if I can factor and cancel. So let's take this function and let's factor it. So I'm going to factor the bottom. The bottom factors into x minus 2, x plus 2. Well, x minus 2 over x minus 2 is 1. So I get 1 over x plus 2. And so there's my new function that I'm going to replace this function with. So as long as x does not equal 2, then these two functions will be equal. So I can take the limit that I started with and I can replace that limit with the limit of the replacement function, 1 over x plus 2, and then I can just evaluate this function as x approaches 2. Well, I know the limit of the top is not going to change, it's just going to be 1, and the bottom, now I can plug 2 in and I get 1 over 2 plus 2, which is 1/4. Okay, so there you have it. There's the replacement theorem in action there. So the limit of this function is actually 1/4. To emphasize this, let me show you a graph of the original function that we started with here. Here's x equal 2. Let's approach 2. Let's see what happens as we get to 2. Alright, so notice this function is not defined at 2. But if you get close to 2 from either side, you'll see you're very close to 1/4, 0.25. Okay? Well, what we really did was we just replaced that function with this function, which is 1 over x plus 2. And now that function actually does have a value at 2, which is 0.25. So those two functions are actually the same except where x is 2. So it turns out that since they're the same everywhere except at 2, we can actually use the second function to get the limit of the first function. And so that's the trick we use. Now I won't do the graphs on the rest of these, but you feel free to graph the original function and the replacement function if you want to. Okay, now this one says find the limit as x approaches -3 of x cubed plus 27 over x squared plus 2x minus 3. Now if you plug -3 in, and you need to do that to verify it, you're going to get 0 over 0. But that's an indeterminate form. So that's a red flag that goes up that says, hey, I need to figure out something to replace this function with. So I'm going to replace it by factoring. Now, review how to factor sum of cubes, but this factors into x plus 3 times x squared minus 3x plus 9. And the bottom factors into x plus 3 times x minus 1. And as long as x does not equal -3, and remember, when you're evaluating a limit, x doesn't equal -3, it just gets very, very close to -3. So as long as x does not equal -3, we can say x plus 3 over x plus 3 is 1, and then we're left with this function. So here's our replacement function. So now when I want to evaluate this original limit down here, I can actually evaluate it by using the replacement function, x squared minus 3x plus 9 over x minus 1, and then I can plug -3 into this function to get my answer. And when I plug -3 into the top, I get 27, or -27, let's see. I get 27 actually. And then when I plug -3 in the bottom, I get -4. So I have 27 over -4, or -27/4. Okay. You can read my summaries there below. It might help you follow some of this. Okay, let's do another one. This one says find the limit of this function as x approaches 0. Well, if you plug 0 in for the top, you're going to get 0. If you plug 0 in for the bottom, you're going to get 0. So here we got an indeterminate form. So let's factor the top. If I factor the top, I can factor an x out, and I get x times x minus 25. The bottom, I can factor 2x out, and I get 2x times x minus 5. Well, as long as x does not equal 0, I can cancel x over x and get 1. So I get x minus 25 over 2 times x minus 5. So I'm going to replace, when I calculate the limit, I'm going to replace the original function with the replacement x minus 25 over x minus 5. And then I plug 0 in, I get -25 over -10, which reduces to +5/2. And here's another one, and I just factored the top, and then I canceled this, and I got x squared plus x plus 1. And then when I used that for my replacement, so I replaced this function with this, and then took the limit as x approaches 1, and I got 3. And of course, the reason I had to do that is because when you plug 1 in up here, you get 0 over 0. Again, an indeterminate form. When you're dealing with radicals or square roots, you're going to use the rationalization technique. Here, if you plug 0 in for this limit, try to evaluate it, you'll get 0 over 0. Okay, so here's the trick. What you want to do is you want to rationalize the numerator. So I have square root of x plus 1 minus 1. I'm going to multiply that by square root of x plus 1 on top and square root of x plus 1 on bottom. Square root of x plus 1 plus 1 on top, square root of x plus 1 plus 1 on bottom. And when I do that, when you multiply these together, you just square the first term, and you get x plus 1 here. And then you square the second term, because you really just have difference of squares, and you get minus 1. And then x plus 1 minus 1 is just x. And then on the bottom, don't multiply this out because that'll mess you up. Just leave it in factored form on the bottom because something's going to cancel. So now you're going to have x over x is 1 as long as, x is not 0. So basically this is our replacement function. So now when I evaluate the limit, I replace it with this, and then I can plug 0 into this, and I get 1 over square root of 1 plus 1, which is just 1 over 2. So I find out the limit is a half. Okay, here's another one. Same thing. If I plug 0 in, I'm going to get 0 over 0, so I can't do that. So I'm going to rationalize it. So I'm going to take the numerator and multiply it by its conjugate. And then when I multiply these two together, I get x plus 2 minus 2, which is just x. And then on the bottom, I get x times this conjugate. And then x over x is 1. And so I get 1 over this. And now I can replace the original function with this replacement function. And then when I plug 0 into that, I get 1 over square root of 2 plus square root of 2, which is 1 over 2 square root of 2. Now make sure when you write that answer, you write it in that form and not as a decimal, because if you write it as a decimal, then that's sort of a red flag for us professors to realize that maybe you found the limit by using the graph or just trying to plug some numbers in. Okay. Here's one more that you can look at. It's very much like the one I just did. And again, the exact form for this is 1 over 2 square root of 3. So you can give this one a try. The only difference is I used h instead of x for the variable. But basically, it's another example of a rationalization technique. Okay? In the next video, I'll continue talking about limits, but I'll strictly talk about one-sided limits.